Alright, so chapter 12.7 is a model for chemical kinetics. It is based off that law that we've already talked about, the collision theory. We talked about it, I think it was back in chapter 3 that we were talking about this, how molecules are constantly moving. Right? And the faster that they're going, the more likely it is, that they are going to react, right? If you have a car that's going 5 miles per hour and it hits something versus a car that's going 500 miles an hour, I know, it's like a really souped up car there. This one is going to get torn apart a lot more and merge with other objects, be it a wall or, another car, a lot better than this one is. And since we're going for chemical reactions, we want them to merge. So the faster it's going, the hotter it is, the more often that we're going to see this happen. This is true because of something that Arrhenius thought of and worked with, and it's called the activation energy. And so here we can see, it's a little diagram I just found on the internet. I've got some molecules here. This is their energy level. This is what they could potentially be at. And we all know that they want low energy. But to do that, they have to overcome this amount of energy. The bonds that they have to break and form new bonds. To break those bonds, I have to put energy in. Right? This amount of energy is called my activation energy. Right there. Okay, the book talks about this reaction when it's going over this. 2BrNO goes to 2NO plus Br2. Alright, and you have your diagrams up there at the top. They look a little bit like this, and I'm not as perfect as they are. Here, okay, from this point up, the amount that it takes from where I start to where I can actually crest that hill is my activation energy of activation, EA. Okay, what I am seeing there, and this is what they have drawn there, is before I have, right here, I guess I'll draw this up here, I have a molecule that looks like O double bonded to N, single bonded to Br. Okay. Here I'm going to have O double bonded to N, but what you're going to start seeing happening here is that this bond between the N and the Br is going to extend. And here is a second one. And these two are going to start forming a bond right there. This extends because we still have that octet rule. Bromine can only have one bond. So here it's more like I have half a bond, and here it's like I have half a bond, and here it's like I have half a bond. So that each of the bromines still only have one bond, but they're sharing that bond between two other molecules. And then as it drops down here, now we're going to get to my ON minus two of those and my Br now. Okay, and that bond is fully formed here now, and it's not part of this molecule anymore. And we know, and since we've got this much energy that it put out, okay, that this is where it was before, this is where it is now, this is exothermic. Okay, so let's go through some of the vocab here. This up here is known as my transition state, where it is kind of halfway through the change that it is going to be making. You've accomplished the hard part. Now it's just got to finish it. It's just got to roll down the hill, and it's also known as the activated complex. All right, so it's kind of right here at this point, all put together in one big complex. It's going to fall back apart. It's not stable. But for that split second, it's like they're all bonded there. Okay. The other thing that we have to think about when we're working with this is the orientation. And I can't spell this, so I've got it. Okay. Orientation. If I have my end BR, right, and my BR hits here. This is the ideal situation, right? My BRs are going to hit together. That's going to let them stick. That's going to let these extend. Everything works out that way. Even if I had it the way that I showed it on the last page and the way that the book shows it, that this moved up to here and this was moving down, those BRs hit each other. If I have something like this happening, I cannot have a reaction, right? My O and my BR do not want to react. So if this runs into this and this runs into this, they are just going to bounce off of each other. If these two never hit each other, then this reaction can never happen. So if I had something like O bound to my N, which had an O, which had a C, which had an N, which had an O, which had a C, which had an N, which had a BR, and then my O, C, N, O, C, N, BR. These would hit each other too soon, and these could never hit each other, right? So this reaction would never, ever happen. The orientation, the way that the molecules are shaped, also play a huge role in whether or not they can hit each other, whether or not the reaction can even happen. Okay, so Arrhenius came up with a mathematical equation to show that this worked, and I'm going to skip over a lot of what they do and just go to the end thing here. He said that the rate of the reaction was equal to A E negative EA over RT. Okay. A in this is my frequency factor. How often do they hit? Okay, my sterics are involved in that. The orientation, everything like that. This is basically, does it have enough energy? Okay, this is what he was trying to prove, that it has to have that it has that that it has to have that activation energy thing. When we use this equation, and they get rid of the E the way that I showed you before, and so you end up with the ln of K is equal to a negative EA over R T, and they put it in so that when you draw a line it works out, plus ln of A. All right. When we plot this, we find that this works most of the time, which shows us that activation energy is true. And sterics are true. Okay. So this isn't used a whole lot anymore because we accept this theory as true, but it's going back to, this is how we prove that that there is this activation energy and that it does play a role and that it is important in what we do. Okay, so that is the activation energy.